All right, let's finish up our chapter with 5.8, geometric sequences and series. So geometric sequence is a sequence, which we learned about before, with a constant ratio between consecutive terms. It's called the common ratio. It means we're multiplying by something, the same something each time. In this first example, you can see, well, the term number, so the first term, second term, third term, fourth term, fifth term, and we just multiply by 3 from the last one. To find that ratio, if it is not obvious, you can always just work backwards and divide. 324 divided by 108 is 3. 108 divided by 36 is 3. 36 divided by 12 is 3. And 12 divided by 4 is 3. That's our common ratio, R, because when we go forwards, we're just multiplying by 3 each time. So sometimes it's obvious. In letter A, it should be somewhat clear that our common ratio is -3. If it's not, -135 divided by 45, 45 divided by -15, -15 divided by 5, they all equal -3. So if you can find that rule, that you're multiplying by the same thing each time, then it's geometric sequence. Now letter B is not obvious. So 6.144 divided by 7.68. We want that to be 7.68 divided by 9.6. And 9.6 divided by 12. Well, if we use our calculator and we divide each one of those, we will get the same ratio of 0.8. So our ratio is 0.8. It's 12 times 0.8, and we can always double check it. 12 times 0.8, 9.6. 9.6 times 0.8, 7.68. So it is looking good. The next one, 122, 145, 168, 191. 191 divided by 168. 168 divided by 145. 145 divided by 122. We want to see if all those ratios are the same, and if they are, then we have a geometric sequence. Well, we got about, well, for our first one, about 1.19. 1.08 divided by 1.45. That's 168. I can't read my own writing. Divided by 1.45 is 1.16. Not the same. So not a geometric sequence. We're not multiplying the same thing each time. It changes. And then the last one, not obvious, especially with fractions like that. 3/4 divided by 3/2. 3/2 divided by 3. 3 divided by 6. Now, when we put these in the calculator, we got to make sure that we're putting them in correctly. So our first one was 3/4, so we can do our fraction. 3/4 divided by, and another fraction, and it was 3/2. Okay? If we don't have the fraction button, you can just put it in parentheses. That'll do the same thing. 3/2, oops, not times, divided by 3.5, which is 1/2, of course. And then 6 divided by 3. Oh, they're all the same. Wait a minute. 3 divided by 6. There we go. So we work backwards They all equal 1/2. So that is our common ratio. Oops. So we're just trying to find what multiplies the next thing. Do you have to divide like this? No, if you can see it, just write it. And some of us probably can. Now the terms of a geometric sequence can be represented by a rule or definition. A recursive definition means they use the last term to get to the next term, like we were just doing. We were multiplying by the same thing each time. So the recursive definition for a geometric sequence is, well, we start with A1, just our first term, whatever it is, and then for the next term, we multiply by the last term, just times our ratio for any n greater than 1. Now, an explicit definition allows you to generate any term by substituting a term number in for the n. If we wanted to find, using this, the 32nd term, well, we'd have to know the 31st before that. And we'd have to know the 30th. And we'd have to know the 29th. So we'd have to go all the way back to the beginning. And we don't want to do that. But for our general explicit definition, and this is the one we're going to use this chapter, a sub n, so any term, is equal to the first term times the ratio to the n minus 1. So the number of the term minus 1. So in letter A, they give us a recursive definition. We want to know the explicit definition. So to get that, we need, the first term and the ratio. Well, in letter A, the first term is 5. Because they tell us that's the first term. So it's 5 times, and the ratio, what we're multiplying by each time, is the 1/2, because it's 1/2 times an minus 1. So the one before it. So that's our common ratio, and then it's just n minus 1 for our general term. Now, if I wanted to find the 32nd term, I could plug in 32 for n and get the 32nd term without having to find all the others. Let's look at letter B, same idea. Our first term is 12, and our ratio, what we're multiplying by the last term, is 1/3. Our equation is a sub n for any term equals a1 times our ratio to the n minus 1. That's changing a recursive into an explicit definition. You need your first term, you need your ratio. On to example 3. Given the geometric sequence, write the explicit rule. So again, to do this, we need two things. We need a1, our first term, and r, our ratio. Now obviously our first term is 14, we can see it. And our ratio, if we look from one term to the next, all we're doing is multiplying by 2. Or, again, if we can't see that, divide one number by the number before it. And you get the same ratio of 2. So our explicit rule is a sub n, or any term, equals a1, 14, times our ratio, 2, to the n minus 1. Geometric sequences are a lot simpler to write than arithmetic sequences because there's really no simplification that needs to be done. Now letter B, same thing. A1 is 7, and moving from one to the next, our common ratio is negative because we oscillate between positive, negative, and it's 5. So a sub n equals a1, our 7, times our ratio, -5, to the n minus 1. And that's our explicit formula there. So again, we could plug in any number we want for n and get that number term. If I wanted to find the 400th term, plug 400 in for n, which we will use that idea in example 4. Phone tree is when one person calls a certain number of people, and then those people call the same number of people, and so on. In the 5th round of calls, 243 people were called. Okay, so we're going to be using, our explicit formula, just like we've been doing. Well, we got to find the rule. So we need A1, and, well, we need our ratio, but that's not obvious. So we'll have to find that. And we know that the A to the, or A5, the 5th term, is 243. Now, what we're saying is our phone tree starts here. At that second level, really. So our A1 is really 3. So now we got to work to get our ratio. So A sub 5, 5 is our n then, times 3, our first term, times r, and again, n is 5, so it's 5 to the minus 1. Again, we know the first term's 3 because, well, there's 3 things in the beginning. We know the 5th term is 243 because it says in the 5th round of calls, 243 people were called. We know our explicit formula. So we substitute in, I need to actually substitute in A5. So 243 equals 3 times r to the 5 minus 1. And now we have to solve this for r, a ratio. Don't do anything over on the left side. We get 3r to the 4th now. First thing we have to do to get r by itself is divide by 3. So we get 81 equals r to the 4th. And then, of course, to get rid of something to the 4th power, we take the 4th root. They cancel out. Our r value, our common ratio, is 3. So our explicit formula is a sub n for any term equals 3 times a ratio of 3 to the n minus 1. So that's our general formula. Now, how many people were called in the 8th round of the phone tree? Well, this one's pretty simple. That means n equals 8. That's our 8th term. So A8 is equal to 3 times 3 to the 8 minus 1. So we just simplify. 3 to the 7th. 3 to the 7th is 2187. And 3 times that is 6,561. And of course, those are people that were called in the 5th round. So we start slow, and if we're multiplying by the same thing each time, the numbers get big quite fast. Now we'll look at geometric series. So remember, series was when we take the sum of all the terms of a sequence. So instead of commas between them, we put plus or minus signs. So find the sum of each geometric sequence to the given term. Oh, forgot to go over this. There is our formula. A ratio can't be 1 because then it'd be the same number and over again, and that's not really a sequence. So we need to find A1, we need to find R, and we need to find N, and then we just substitute it into that formula. So S sub 8, and that's what it says we're looking for, is equal to A1, which is 1, times 1 minus our R. And if we look at this, 1 to 2, 2 to 4, we're multiplying by 2 each time. So that's our common ratio. So it'd be 2 to the 8, because we're looking at the 8th term, the sum of the 8 terms, over 1 minus 2. Sorry, our n was 8 because we wanted the 8th term. So now we just work through that formula. So it's 1 times 1 minus 2 to the 8th is 256. Of course, 1 times anything is just that same thing. So 1 minus 256 is negative 255 over negative 1. So our sum is 255 of the first 8 terms. And that's all we're looking at. We're just applying this formula. Again, a formula you don't have to memorize. We will give you for the test and the final exam. Now, letter B, same idea. We need A1, we need R, and we need our N. Well, A1 is very clear to see. It's 2. That's our first term. Our R, we're going from 2 to 6, 6 to 18, 18 to 4 or 54. So it's 3. However, it's also negative because we go from positive to negative to positive to negative. And we want the 11th term. So that is our N, or the sum of the first 11 terms, I should say. So S sub 11 is A1 times 1 minus a common ratio to the 11th power, Rn, over 1 minus a negative 3. Obviously, negatives make a difference, and we have to do our order of operations. We do in the parentheses first, and inside the parentheses, we do the exponents first. So we have negative 3 to the 11th power, and it's still minus that, and that's negative 177,147. So up our other parentheses, over 1 minus a negative 3 is 1 plus positive 3. So that's equal to 2 times, again, this is just like plus as well. So 177,148 over 4 gives us a grand total of 88,574. Again, 11 terms, just went 11 numbers across, and we got 88,000. It builds up fast. Let's take a look at the U-try. So now the numbers are going down, 81, 27, 9, 3. So our ratio has to be less than 1. So again, we look for our A1, our R, and our N. Well, A1 is 81. That's pretty clear. Our ratio, as we go across, isn't 3, because we're not dividing, we're multiplying. So our ratio would have to be 1/3. And again, we can see that 3 over 9 equal to 9 over 27 equal to 27 over 81, and they're all equal to 1/3. So that's our ratio. And we want the sum of the first 200 terms. However, the numbers are getting smaller, so it's not going to be a huge sum. So let's use our formula. S sub 200 equals our A1 times 1 minus our ratio to the N, 200, over 2/3. Oops, not 2/3. Not yet, anyways. 1 minus 1/3. So we go step by step. 81 times 1 minus 1/3 to the 2,000, or 200, I should say. Now, when we do 1/3 to the 200, it's going to be such a small number. 3.7 times 10 to the negative 96th. So it's pretty much 0. So this is really 1 minus 0 over 2/3. So that's 81 times 1 over 2/3, which is 81 over 2/3. And if we divide that using our calculator, or we multiply by the reciprocal, we get 243 over 2 as our sum. We can leave it like that, or we can do 121.5. That's fine as well. So that's our sum for the first 200 terms of that geometric series. Let's move on to example 6. We have to write the following from sigma notation into expanded form, and then we gotta find the sum. So if we're looking at our term here, we have n1 or n equals 1 to 5. So we have 5 terms. So n equals 1, n equals 2, n equals 3, n equals 4, and then n equals 5. So we just substitute those in the formula. 1/2 of 3 times 1 minus 1. 1/2 3 times 2 minus 1. 1/2 times 3 to the 3 minus 1. 1/2 times 3 to the 4 minus 1. And 1/2 times 3 of 5 minus 1. So we need to find each of those individually. However, if we use our calculator and we look at a table, we can find these values much easier. So to do that, we need to put in our explicit formula, our A1, 1/2, times our ratio to the n minus 1, but we can't use n, we have to use x. Then, when you hit second graph, you go to the table, and if we substitute in 1 for x, or 1 for n, we get 1/2. 2 gives us 3/2, 3 gives us 9/2, 4 gives us 27/2, and, oops, wrong way, and 5 gives us 81/2. Or we get to type the whole thing in our calculator, that works as well. Either way, we get 1/2, 3/2, 9/2, 27/2, and 81/2. So we add those 5 terms up. And when we add them all up, the sum of these 5 terms is 121/2, or 60.5 if you prefer. Let's look at this next one. We got another summation notation that we need to find the sum. We don't necessarily need to find each term. We could, but I don't think we need to. What we need to use our sum formula is A1, our ratio, and the number of terms. Can we figure those out? Well, A1 is 3. That's just part of our explicit formula. Our range is 2/3. And our n, well, we've 1 to 7, so we have 7 terms. So we can just throw that into our formula. So S sub 7 is equal to 3 times 1 minus 2/3 to the 7th over 1 minus 2/3. So we just need to raise this to the 7th power. We get 1 minus 128 over 2187. And now that's over 1/3. 1 minus that fraction times 3 divided by 1/3. And we get 2059 over 243. So that is our sum of those 7 terms. And again, we could write them out. N equals 1, so 3 times 2/3, so the 1 minus 1. And n equals 2. And so on, all the way down to n equals 7, and then add them up. But that's not the quickest way to go about it. It's much easier to use the formula to find our summations. So let's try 2 more in example 7, but now we have to write the summation notation and then find the sum. So it's kind of backwards from what we just did. So again, to find our sum, we need A1, N, and our common ratio. Well, in this first example, letter A, A1 is 4. We can see that. Going from one term to the next, it's clear that our ratio is 3. And how many numbers are there? Well, there's 5, so that's our N. So first, in sigma notation, N equals 1 to 5 of 4 times our ratio to the N minus 1. And again, that's just our explicit formula for geometric sequence. So that's our summation notation. But now let's actually find our sum. So again, we're going to use that same formula. So S sub n equals a sub 1 times 1 minus r to the n over 1 minus r. So in this case, it would be S sub 5. So we're looking for the sum of the first 5 terms. A1 was 4. Our ratio is 3. So that's to the 4th power over 1 minus our ratio. And then we just simplify. So that's 1 minus, that 4 should be a 5. So 1 minus 243 over negative 2, which is 2 times negative 242 over negative 2, which gives us the grand total of 484. So that's our sum. That's our summation notation. So, and of course, we could have just added up those 5 numbers, but if we have a lot more numbers than that, we can't do it that way. All right, let's look at this last one, letter B. We need A1, we need R, and we need N. A1 is 64. Our N, well, we have 7 numbers. Now our ratio is not obvious. We're dividing by 2, but we don't divide with our geometric sequences or series. We multiply, I guess, by the reciprocal. So really we're multiplying by 1/2. Or if we just divide 1 by the number before it, we can see that those are all going to be 1/2. So that is our ratio. So our summation notation is from n equals 1 to 7, because there's 7 terms. Starting with 64, our ratio is 1/2 to the n minus 1. So that's our summation notation. But our actual sum, we get S sub 7 equals 64 times 1 minus 1 over 2, to the 7th, over 1 minus 1 over 2. This is 64 times 1 minus 1 over 128 over 1/2. And we simplify that all the way down, we get 127. It's not a huge sum because our numbers are decreasing. And that's what's going to happen. And those are geometric sequences and series.